In this video, we will talk about limits of functions. First, we'll review accumulation points and then define limits. Then we will have a strategy of proof of limits. We'll talk about the relation of limits of functions and limits of sequences, as well as a corollary that defines the uniqueness of a limit and a theorem to show the criteria to show a limit does not exist. We'll go over theorems for sum, product, multiples, quotients of limits, and then we'll also look at one-sided limits. We will start by reviewing the definition of an accumulation point. Let S be a subset of real numbers. So here I've drawn on a real number line an open interval which I'll call S. That's our subset of real numbers. A point X in the real numbers is an accumulation point, also called a limit point or cluster point of S, if every deleted neighborhood of X contains a point of S. So in other words, here are three different points. And in each of these points, I could draw a deleted neighborhood. So a small neighborhood where if I delete the point X, so if I delete X1, I still have points in this neighborhood contained in S. So this is obvious. And this point, it's a little bit closer to the border, but it's obvious. You can draw a deleted neighborhood. And also, just a note, it's not that I can draw a deleted a little neighborhood. It's that every deleted neighborhood, no matter how small I want to make it, will contain a point in S. And so here, even on the boundary, no matter how small I make it, I can make it infinitesimally small, but as long as X, because X3 is on the boundary, any neighborhood is going to have something just a tiny bit, no matter how small, it's going to have something even a tiny bit less than X3, which is in the neighborhood of S. So the idea of an accumulation point or a limit point is you can get the elements of S can get arbitrarily close to your accumulation points. Whereas here, I have a point outside of S, and for this X, there are epsilons, any epsilon less than this distance here, where I can get this epsilon distance away from any point of S. So this point is not a limit point. X can escape S. For the definition of a limit, let's say we have a function from a domain to the real numbers, and C is an accumulation point of the domain. A real number L is a limit of f at C if for each epsilon greater than 0, there exists a delta greater than 0, such that f of x minus L, the difference between your function and L, is less than epsilon whenever x is in the domain and the distance from what you plug into x minus c is less than delta. And we write the limit of f of x is equal to L. This is where a drawing could be helpful, and also this definition of limit is totally consistent with what you learned in first year calculus. So we have this drawing f of x, right? And so here's our x values, here's our graph. So what we're saying is epsilon and delta, these are things that we're going to shrink down as they approach 0. We're going to make them infinitesimally small, but they're going to be greater than 0. So this function minus L is extremely small. So the function starts to approach L. F of x and L get the distance between them is very small. They approach 0. Whenever x approaches C, when the distance between x and C get very small. So as x approaches C, or x minus C is extremely small, then f of x minus L also gets extremely small. And the idea is you can get arbitrarily close to the limit by making epsilon really small. But as you change epsilon, I'll have to give you different deltas, presumably deltas that are even closer to C, our limit, in order to get arbitrarily close to L. But I can always do that. I can always, no matter what epsilon you give me, I can always give you a delta that'll satisfy this condition. And the question is, well, how close does x need to be to C? In other words, in this interval, C minus D, C plus D, how close, how small can D be such that f of x is in this very small interval, L minus epsilon, L plus epsilon? One other note here, because our definition of limit has this less than sign, and it's a strictly less than, it can't be equal, that has the effect of making x close to c, but deleting the point x equals c. In other words, there's no equality here. So what that means is, in this definition of limit, what's important is what happens near to c. It doesn't matter what happens at x equals c. In other words, f of c need not be defined. You can still have a limit at f of c. Here's a theorem that gives us another way of looking at this limit definition in terms of neighborhoods. So again, we have f as a function from d to r. C is an accumulation point. Then the limit of x approaches c of f of x is equal to L. If and only if for each neighborhood v of L, so this v is the L plus epsilon, L minus epsilon, there exists a deleted neighborhood of u such that, and u is this neighborhood c minus d, c plus d without c, f of u intersect d, so the image of u intersect d, of u, is contained in v. So in other words, for this small neighborhood, which is the L plus epsilon, L minus epsilon, this neighborhood here, we can find a neighborhood in the domain that the image of this neighborhood will stay within our neighborhood V. So again, another way of looking at the limit definition, looking at it in terms of neighborhoods. So we have this strategy for a proof of limits, and this is very similar to the strategy we use when we're proving limits of sequences. The first step is to guess a value for the limit using techniques from first-year calculus. Then we're going to look at the inequality f of x minus L is less than epsilon, and we're basically going to work with it until we have the form x minus c is equal to something in terms of epsilon. Again, x minus c, so that something in terms of epsilon is going to be our delta. So then our proof template is going to be given epsilon greater than 0, take delta equal to, and again we plug in the something in terms of epsilon, and then we're going to say note or notice, this is actually part of the proof template, which you write, note, and then plug in your calculations in reverse, these calculations you did over here in step 2. And you're going to finish with, therefore, x minus c less than delta implies that f of x minus L is less than epsilon, and that's exactly the definition for the limit. One last note, it is worth your time to look at this strategy and see how you're satisfying this definition of limit. Our first example is to let k be a real number, and we are going to define the constant function f of x is equal to k for all real numbers x. We want to show for any real number c, the limit as x approaches c, f of x is equal to k. So the first step of my proof template is to guess a value for the limit. We don't really have to guess, and that's exactly what we're trying to prove. So f of c is equal to k. Next, we're going to reduce the inequality f of x minus L is less than epsilon. So plugging in f of x, given our formula, f of x is equal to k minus L, and our proposed limit is k, and that's less than epsilon. So what we have is 0 is less than epsilon. Normally we're going to use this criteria, what we get epsilon, we have some criteria, except the only thing we have here is epsilon is greater than 0, which is actually what we started with. So that means that epsilon is greater than 0 is satisfied for all delta greater than 0. So in other words, normally we plug in delta equals something in terms of c, but in this case, every delta will satisfy this condition. So normally we have something like x minus c is less than delta, but since this is always satisfied, we can just let delta equal 1 or any other real number. So our proof is going to go, and you do want to note how the proof basically echoes our definition of the limit. But given epsilon greater than 0, let's take delta equal to 1. Then we're going to note delta equals to 1 and epsilon greater than 0, and 0 is equal to, and using these calculations backwards, k, the absolute value of k minus k, which is equal to f of x minus L, and then where f of x is equal to k and L is equal to k. And this definition here, by all of this, that implies that the limit of f of x as x approaches c is equal to L. We're going to do another example where we're not dealing with the constant function, which is kind of strange. And here we don't have to guess a value for the limit because we're told what value we want to prove. My next step is to look at the inequality f of x minus L is less than epsilon. So I have f of x is equal to 2x, and then I have my proposed limit is 5 is less than epsilon. And I want to reduce this or solve this until I have the form x minus c is equal to something in terms of epsilon. So algebra, I do some algebra here, and eventually I get x minus 3 is less than epsilon over 2. So this is going to be my delta. And now I'm ready to plug into my proof template. So given epsilon greater than 0, take delta and I plug in what it is over here that I solved for my something in terms of epsilon. So that's epsilon over 2. And then I'm going to note, I guess I wrote notice, but note that epsilon over 2 is greater than, and I'm going to start these calculations backwards. Epsilon over 2 is greater than x minus 3, which implies that epsilon is greater than 2 times x minus 3, which implies that epsilon is greater than 2x minus 6, which implies that epsilon is greater than 2x minus 1 minus 5. So if we compare this line to what we have here, L is a limit of f at c if for every epsilon greater than 0 there exists a delta which we have identified such that f of x minus L is greater than epsilon. So this is f of x minus L is less than epsilon whenever x minus c is less than delta, which we have somewhere here, over here, x minus c is, we have it somewhere, then we write the limit of f of x is equal to L. So that means the limit of this f of x is equal to L. Here is another example. Let f of x is equal to 2x squared minus 3x plus 1 divided by x minus 1 for x not equal to 1. And f of 1 is equal to 5. We want to find the limit of f of x as x approaches c. The first thing we want to do is guess a value for the limit. So I'm going to look at 2x squared minus 3x plus 1 over x minus 1. I factor, and then I can see I can cancel this out, and I get 2x minus 1. So as x, what did we want? As x approaches c. In this case, c is equal to 1. So as x approaches 1, we have f of x is equal to 2 times 1 minus 1 is equal to 1. So this will be my guess for my limit. And I note that f of 1 is equal to 5. But remember, we really don't care what happens at f of x, right? F of c doesn't need to be defined. It doesn't even need to, be 1. We're just fine. Our next step is to look at f of x minus L is less than epsilon and get it into the form x minus c is something in terms of epsilon. So f of x minus L, our f of x is going to be 2x. Our proposed limit is 1 less than epsilon, and we want to manipulate this until we get x minus c, something in terms of epsilon. So I do the algebra, combining the two negative 2's. I pull out the 2, and then I can divide by 2 on each side, and I get x minus c, which is exactly what I wanted, is less than something in terms of epsilon, epsilon over 2. And we're going to take this something in terms of epsilon and let d equal epsilon over 2. So plugging into our proof template, given epsilon greater than 0 and delta, plugging in our something in terms of epsilon, delta is equal to epsilon over 2, we want to note that delta is equal to epsilon over 2 and is greater than x minus 1. And now we're starting all these calculations backwards until finally we get to f of x minus L is also less than epsilon, which implies that the limit of our function is equal to 1. Our next proof, let f of x equals x squared plus 2x plus 6. We want to prove the limit as x approaches 3 of f of x is equal to 21. Like one of the previous problems, at this point we don't have to guess a limit because they tell us what they want us to prove. Our next step is to reduce this inequality, f of x minus L is less than epsilon, into something that looks like the form x minus c is equal to something in terms of epsilon. So f of x minus L, so here's my f of x, x squared plus 2x plus 6, minus L, and my proposed limit is 21, is less than epsilon. I do this algebraic calculation until I get x minus c, c being our limit 3, is less than something in terms of epsilon. So I'm nearly there, except that ideally I wouldn't still have this x. So I need to do something about this x. So I'm going to look at this absolute value of x plus 5, which I'm going to rewrite as x minus 3 plus 8 for reasons that you'll see later, but except that I'm going to say that x minus 3 is no accident. That's actually x minus c. And that's less than or equal to x minus 3 plus absolute value of 8 by the triangle inequality. And the next thing I'm going to do is I'm going to assume x minus 3, which is my x minus c, which should be less than delta. I'm going to assume that delta is very small, in which case x minus 3 will be less than 1. And remember, we have delta very small because we're looking at x approaching 3. So if this is c, no one's worried about c plus or minus delta, a large delta way out here. We're looking at c as we're looking at approaching c, so delta gets very small. And because I have this assumption, this explicit assumption that delta is going to be less than 1, I'm going to underline it so I remember to take it into account later when I assign my delta, which will mean that my x minus 3 is less than 1 plus absolute value of 8. So the x plus 5 is going to be ending up less than or equal to 9. So now I have x minus 3 is less than epsilon over x plus 5, which we want to be less than 9. So x minus 3 is less than epsilon over 9. So now I'm going to let delta equal my minimum of 1, since I had this assumption that delta was less than 1, and epsilon over 9. Plugging it into my proof template, I want given epsilon is greater than 0 and delta, and then plug in my delta. So given epsilon greater than 0, take delta equals the minimum of 1 and epsilon over 9. Then I want to notice, and I want to plug in my calculation in reverse and finish with this f of x minus L is less than epsilon. So I'm going to say notice, then x minus 3 is less than delta means that x minus 3 is less than 1 and x minus 3 is less than epsilon over 9. So I have x minus 3 is less than 1, which is going to give us, working this backwards, the absolute value of 1 plus the absolute value of 8 is equal to 9, which is then greater than or equal to x minus 3 plus absolute value of 8. And that's because, well, anyway, I'm just working backwards, which is greater than or equal to x minus 3 plus 8, which is equal to x plus 5. So what I can take from this line is that x plus 5 is going to be less than or equal to 9. Then going from here, I have, or going from here, x plus 5 times x minus 3 is less than 9 times, and then taking x minus 3 equal to delta, epsilon over 9, which is equal to epsilon. So I have my x plus 5, x minus 3 is less than epsilon, and then from there I can then work backwards so that my x plus 5, x minus 3 gets to be x squared plus 2x plus 6 minus 2 is less than epsilon. So this problem was a little more complicated, and which is why I have a note for quadratics. And the reason why it was complicated is because when we solved for x minus c in terms of epsilon, we still had this x term here, x plus 5. So what we did is we wrote x plus 5 in terms of x minus 3 plus whatever else we needed to add to it. So then this x minus 3 here, we assumed when it was very small, because this x minus 3, this x minus c is going to be less than delta, we take this for our delta, and we're going to assume it's less than 1. So this is one assumption on delta. And then when we solve for this, then we get another assumption on delta, which is x minus 3 is less than epsilon. So we need to take delta equal to the minimum of 1 and epsilon over 9. So again, that was kind of the extra added thing we needed to do for this quadratic. Here's another example in much the same spirit as the last. You want to find a delta greater than 0 so that x minus 2 is less than delta implies that x squared plus x minus 6 is less than 1. So we factor out our x squared plus x minus 6, so we have this x minus 2 term. And much like we did in the last example, we're going to assume that delta is less than 1 because delta is really small because we're approaching x equals c. So that means this part here, x minus 2 is less than 1. Now when we consider x plus 3, we're going to expand that to x minus 2. The significance is x minus 2 is less than delta, plus 5. And this is the same trick we used in the previous example. And then by the triangle inequality, and if you don't know the triangle inequality by now, this is the time to learn it. You know, absolute value of a plus b is less than or equal to absolute value of a plus absolute value of b. So I have my a is equal to x minus 2, and my b is 5. So here, 5, the absolute value of 5 is just 5. So then what I get is that is equal to 6. Because, this should be less than or equal to 6 because x minus 2 is less than 1 and 5 is equal to 5. And then finally what I have is this x plus 3 is less than or equal to 6. And when I come back to look at the x plus 3, x times 2, well, that's going to be less than or equal to, here I have 6, and then I have my x plus 2, which is delta, which is less than or equal to 1. So what I get is delta is less than or equal to 1/6, so I'm just going to take delta equal to 1/6. Our next topic is the sequential criterion for limits, and what this section does is it relates the limits of functions, which we are looking at now, to the limits of sequences, which we had looked at in a previous video. And the theorem is if we let f go from d to the real numbers and let c be an accumulation point of d. So we have the some limit as x approaches this c, this accumulation point. Then the limit as x approaches c of f of x is equal to L if and only if for every sequence Sn in D that converges to c with the Sn not equal to c for all n, then the sequence f of Sn converges to L. I kind of have this drawing here to help me out with the ideas. So I have a function, f of x, and then if I look at as x approaches c, this is my accumulation point, and I'm saying the limit of f of x is equal to L. If and only if for every sequence Sn in D that converges to c with Sn not equal to c for all n. So in other words, here I have a sequence converging to c. I have S1, S2, S3, they're getting closer and closer, and you have the sequence converging to c, but never equal to c. As this sequence converges to c, we want the sequence of f of the sequence. So here's f of S1 in blue, f of S2, f of S3, we're getting closer and closer. F of Sn is getting closer to L. And that's what this is saying. So it relates this sequence converging to C means f of the sequence converges to L. And then we can say the limit of x approaches C of f of x is equal to L. Before we do some examples, there's a corollary and theorem we need to cover. The first corollary is uniqueness of the limit. So if f is a function from D to R and C is an accumulation point of D, then f can only have one limit at C. So kind of a little picture here. You remember in ordinary first year calculus, if you looked at x equals c and you want to know if a function converged at x equals c, the limit of your function as x approaches c from the left-hand side, as you approach this way, has to equal the limit of f of x as x approaches c from the right-hand side. Remember, these two have to be equal because the limit's unique. You can't have two different limits. So if these were not equal, the sequence was not convergent. Similarly here, if you have two sequences, here I have a blue sequence that's converging to x equals c, and here I have a green sequence that's also converging to x equals c. So for my sequence f to be convergent, the limit of f of my blue sequence, as the blue sequence converges to c, has to equal the limit of f of my green sequence as the green sequence converges to C. Because these two are both converging to C, that means the limits of the two sequences need to be equal. Otherwise, the function is considered not convergent. So this here is the significance of the uniqueness of the limit as far as looking at the sequences, the sequential criterion for limits. Next, we have a theorem to show the criteria to show a limit does not exist. So we have let f be a function from D to R, and C is an accumulation point of D. Then the following are equivalent. F does not have a limit at C, and there exists a sequence Sn and D with each Sn not equal to C such that Sn converges to C. So Sn converges to C, but f of Sn is not convergent in R. So for the sequential criterion for limits, we have two theorems and a corollary. So first, this theorem here, it tells us when a function f of x converges to L as x approaches C. And the criterion for this, how do we know that the function converges? Well, for every sequence Sn that converges to C, then f of Sn will converge to L. The second theorem is almost the opposite of the first theorem. It tells us when a limit does not exist, when the function does not converge. And when does it not converge? Well, when Sn converges to C, very similar to this first theorem, f of Sn does not converge. So it's the opposite of here. So if this criteria is not met, we know the limit does not exist. And last, we have this corollary uniqueness of the limit. And we discussed how uniqueness gives us this requirement that if we have two sequences that approach C, then the limit of f of Sn must be equal. If they're not equal, that means the function does not converge. So in effect, the fact that limits are unique also gives us another way of determining when a sequence does not converge. Now it's time for an example. Consider the function f of x is equal to 1 over x for x greater than 0. Using the last theorem, so this one here, show that the limit as x approaches 0 of f of x does not exist. This is probably a good time for an example. So let's consider the function f of x is equal to sine of 1 over x for x greater than 0. We want to show the limit of f of x as x approaches 0 does not exist. And I have this table over here from your book that's really useful because it tells you when you look at sine of n pi over 2, you get for n equals 0, the value 0. For n equals 1, you get 1. For n equals 2, you get 0. And n equals 3, you get negative 1. And then the k just means it's periodic, so you keep cycling through these values. In other words, you don't converge. So we're going to use this. And we're going to use this table along with this theorem, the criteria to show a limit does not exist. We want to find a sequence, Sn, that converges to C. In this case, C, our limit is 0 as x approaches 0. And functions such as 1 over n will converge to 0. But we want to show f of Sn is not convergent. So we're going to use this because n pi over 2 is not convergent. But we're going to plug it into f, and since f has this 1 over x, we're going to use the reciprocal of n pi over 2. So our Sn is going to be 2 over n pi. And we can see the limit. As I said, we'll pull out the 2 pi. So Sn is essentially 2 pi times 1 over n, and 1 over n as n approaches infinity approaches 0. So we can see the limit of Sn is equal to 0. So we're doing pretty good here. I did write out the first few terms of Sn, just so that we can show that f of Sn will not converge. So plugging in these values into f, I have f of S1 is equal to sine of pi over 2, remember I have the reciprocal, which is equal to 1, f of S2, which is 1 over pi, using the reciprocal, sine of pi, which is 0, and then f of S3 is negative 1, f of S4 is equal to 0, we can go f of S5, etc., and we're just going to cycle through here. So we can see that this does not converge, which means that f equals sine of 1 over x does not have a limit at x equals 0. I've done this problem again and proven that the limit of f of x does not exist And in this time, I use the corollary here, the uniqueness of the limit, as well as the definition of limit. So I introduced Sn, another sequence of 1 over n pi, so that the limit as n approaches 0 of Sn is equal to 0. And then I looked at the limit of f of Sn, and so this is the limit of sine of n over pi, right, which is equal to 0. I compared that to Tn, which is another sequence whose limit is equal to 0, but the limit of f of Tn is equal to 1. And since the limit of f of Sn and the limit of f of Tn do not equal each other, and the limit must be unique, it must be that the limit as x approaches 0 of f of x does not exist. The next theorem talks about the sum, product, multiple, and quotient of limits. So if we have two functions, f and g, from d to r, and c is an accumulation point of d, then if the limit of f of x as x approaches c is equal to L, and the limit of g of x as x approaches c is equal to m, and k is a real number, then the limit as x approaches c of f plus g is equal to L plus m. The limit of f times g is equal to L times m. The limit of kf is equal to k times the limit. And if g of x does not equal to 0, then the limit of f over g is equal to L divided by m. We will do the proof of the sum, and the proof of the other parts are similar. I am going to use the sequential criterion for limits for this proof. So that theorem is over here. That essentially says the limit of f of x is equal to L as x approaches c, if and only if every sequence Sn that converges to c means that f of Sn converges to L. So I'm going to start by constructing or designate a sequence Sn. So that's going to be a sequence in D that converges to C. Then by the sequential criterion for limits, that means the limit of f of Sn must equal to L, and the limit of g of Sn must equal to m. And again, using the sequential criterion for limits, if I want to prove that the limit of f plus g as x approaches c is equal to L plus m, that will be equivalent to proving that the limit of f plus g of s of n is equal to L plus m. Now that I have everything in terms of limits of these sequences, it'd be really helpful if I could remember those limit theorems for sequences, and I have the appropriate one written here, that when we were studying sequences in the previous video, we said the limit of Sn plus Tn is equal to the limit of Sn plus limit of Tn. We can use this theorem here on this expression here, and we'll get the limit of f plus g of s of n is equal to the limit of f of s of n plus g of s of n, which is equal to the limit of f of s of n plus limit of g of s of n, and then by definition over here we are given that's equal to L plus m, and our proof is done. And just a reminder, what this did, this sequential criterion for limits, it let us rephrase this question about limits in terms of sequences, and then we could use our limit theorem for sequences in order to prove the limit of functions. An example of using this theorem, since the limit of x equals c when x approaches c, it follows from the product formula that the limit of x squared as x approaches c is equal to c squared, and by induction we can obtain the limit of x to the n as x approaches c as c to the n. So combining this with the sum and multiple formulas, we get formulas for polynomials and for any real number c. So the limit of p of x, a polynomial in terms of x as x approaches c, is the polynomial with c plugged in for x. And we can use this to evaluate the limit as x approaches 1 of x squared plus 2x minus 5 divided by x squared plus 3x minus 5. And according to this right here, it says the limit as x approaches c of the polynomial we can just plug in c. So we can plug in c on top, plug it in on bottom, and we get our answer. Our next example is to evaluate the limit as x approaches 1 of f of x is equal to 2x squared minus 3x plus 1 divided by x minus 1. And just note, because it says evaluate, I'm thinking that we want to use this theorem to evaluate the limit. We're not trying to prove a limit. I kind of went from this step to this step, skipping a few things, so over here I wrote it out in more painful detail. So the limit as x approaches 1, I have 2x minus 1. By this part of the theorem, I can consider this f, and this my function of g, so I can separate this out to the limit of 2x and the limit of minus 1. And then so that's what I have here. And then to go, oh, no, not quite. So to go from here to here, I used this part of the theorem when I have a constant k, and I can pull the constant out. So that's what I did here. So now I have 2 times the limit of x as x approaches 1 minus the limit of 1 as x approaches 1. So the limit of x as x approaches 1 is 1. So I have 2 times 1 minus 1. So my final answer is 1. And again, I didn't do a proof, but I was evaluating the limit, and I was using this theorem here. Now we've covered the topics on this slide, and the first thing we did was we defined a limit of a function, a limit of f at c. We talked about strategies for proving that a limit L is a limit of f of x as x approaches c. We talked about the sequential criterion for limits, and that relates the limits of functions to limits of sequences. So we can convert a question about the limit of a function by looking at a sequence within the function and then proving the limit of the sequence. We showed 3 ways of determining if a limit exists or does not exist. We talked about this theorem that talked about the sum, product, multiples, and quotients of limits. And then last, we talked about one-sided limits and limits at infinity. Actually, I lied. We hadn't talked about one-sided limits. So let me give you the definition. And this is very much like one-sided limits in first-year calculus. So the domain, actually, it is exactly alike. So the domain of f is on the open interval AB. Then we can talk about the limit as x approaches a. And then we sometimes can talk about approaching a from the positive side, which is called the right-hand limit. So the limit as x approaches from the positive side, so from the right of a, is equal to L if and only if for every epsilon there exists a delta greater than 0, such that f of x minus L is less than epsilon whenever x is in the interval AB and x is between a and a plus delta. So it's the same definition, except now we're only looking at the right-hand side. And then the limit as x approaches c exists only if the left and the right-hand side limits are equal, just like first-year calculus. So we hadn't actually talked about this, but we did use this last fact in one of our previous examples. So now that we've covered all the topics, I have 4 questions for you to try for review. So pause the video, give them a try, and on the next slide, I will have solutions. Here are the solutions for the 4 problems. And that's it for this video. Thank you for watching.